passive device free multi-point CSI localization and obfuscation with randomized filtering. University of Brescia, Italy. Abstract. The use of channel state information (CSI) as a means of sensing the environment through Wi-Fi communications, and in particular to calculate the position of unaware people, is moving from feasibility studies to high precision applications. The work we presented in this paper explores how the use of multi-localization receivers can enhance the precision and robustness of device-free CSI-based localization with a method based on the state-of-art convolution neural network. Next, we discuss how the randomized pre-filtering at the transmitter can hide the information that the CSI carries on the location of one person indoor, formalizing the manipulation techniques. Results are presented discussing two different ways of exploiting the multi-receiver redundancy and how, in any case, properly randomized pre-distortion at the transmitter can prevent localization even if the attack is carried out with multiple location devices. Receivers controlled by the attacker. Introduce and state-of-the-art sensing as a side service of Wi-Fi is becoming an industrial reality, and in particular channel state information CSI-based localization is attracting attention for device-free indoor positioning. This research field was opened about 10 years ago by seminar works like 1 to 4. Then the academic community indulged on many variations of the topic, hinting to the possibility of identifying activities or gestures 5th and 6th, seeking healthcare applications 7th, and many others. The most recent trend exploiting machine learning and artificial intelligence (AI) 8 to 11 to compensate the difficulty of finding analytic models with the power of supervised learning techniques for classification purpose. Often involve deep learning or reinforced learning. The recent survey 12 can compensate for the interested reader. What we cannot discuss here for lack of space. The two topics receive instead little attention. If and how multi-point reception can improve the reliability of CSI-based localization, and how much localization impacts on privacy of people. Although the scarce attention to the first may look surprising, we could find only 2 works on the topic. The author of the 13 proposed to the massive multiple-point input-output MIMO technologies to improve the quality of CSI-based localization with the neural network. The work exploits up to 64 antennas, but indeed with a single logical measurement point. The work focused on the learning technology and assumes that there is a service dedicated to localization. For example, specific frames are transmitted dedicated only to localization. Thus, this work should be compared mainly with the technologies dedicated to localization as those based on time of flight like 14, rather than sensing as a side effect of Wi-Fi communications. The research in the 15 is indeed the only one that has similarities with our contribution, though it focused on localization of a device and not as we do on the localization of the person who does not carry a device. The works build on the concept and channel charting 16, which lends to the possibility of semi-autonomous training because it uses differential positions and differential CSIs. Hence, assuming a slowly changing channels with a CSI sampling that respect a Nyquist theorem, a conditional that, for instance, cannot be assumed if Wi-Fi traffic sporadic. or to detect the presence of the person in a room, a condition that implies a sort of discontinuity in the CSI. Just as surprising is the overlooking of privacy implications, which has been addressed only very recently by our and other groups, 17 and 23. A first idea that comes to mind is using a reactive jamming device that selectively kills the frames that belong to the localization attack, adapting for instance techniques like 1718. To the best of our knowledge, this idea has never been explored in the literature, maybe because it kills traffic. Thus, if the frames used for localization also carry user data, communications will be heavily hampered. Additionally, such a technique requires to now know that an attack is underway and the ability to identify the frames used for localization. Otherwise, it would become simply a jamming denial of service. A system to encounter Wi-Fi sensing was originally proposed in 20 to prevent gesture recognition. Similar to 22, this system is based on the independent device that relies frames with the goals of superimposing an additional reflection of the signal that obfuscate the information imprinted by the environment on frames, differently from the more common jamming that superimpose a different signal, sometimes just a noise, with the goal of killing the frame reception. The works that lay the foundations of the paper are 1921 to 22. In the first two, we proposed for the first time a technique of obfuscate or hide the information carried by the CSI that enables localization, focusing on passive attacks. For example, those where the attack controls only the receiver. The core idea is randomly distort the transmitted frames so that the CSI at the receiver looks like the one of the signal that has propagated through a different environment, unrelated to the one in which sensing is performed. In the third one, we tackled the problem of counting active attacks. For example, those where the attacker controls both the transmitter and the localization receiver. In this case, countermeasures cannot be based on the pre-distortion of the transmitted frames because transmitted frames are controlled by the attacker. The solution we proposed is based on the fast relay road, ideally an intelligent reflective surface like those discussed in 24, which introduces a time-varying additional reflection in the electromagnetic environment that prevent a localization device to pinpoint the position of the person. Finally, exploiting techniques similar to those used in 21 to 23 manipulate the CSI, the goal of avoiding device radiometric fingerprinting and preventing impersonation attacks. The topic of the paper is not localization, but if a person holds a Wi-Fi device, a double attack identifying the device. Figure 1. In the considered scenario, the attack can collect the CSI data simultaneously at the 5 receivers RX1 to RX5, locate a victim standing in one of 80 possible target locations, and the location of the person is more than possibility. The contributions of the paper in the context of localization and if obfuscate are two. First, we present the first experiment study that shows how using multiple location devices, the precision of localization can be improved. Second, we show that also in these conditions, the privacy of user can be preserved with the refinement of CSI randomization techniques we first introduced in 1921 not only protect users from localization attacks, but also preserving the communication performance. Second, attack models on the scenario. In this section, we quickly summarize the reference attack model that can be used to monitor the activities and the position of unaware people through the opportunistic reuse of the Wi-Fi signals pervading modern environments. Then we describe how we implemented this model in our laboratory. A. Attack model. The attack model is shown in figure 1. We assume that the attacker, for example, an employer whose goal is combating registration, for example, an employer whose goal is circumventing registration on employee monitoring, can control multiple devices with the ability to extract CSI data from the received Wi-Fi frames. The large availability of extremely cheap and small platforms that can be converted into sensing nodes, like the Raspberry Pi 25, makes this feasible and cheap even on a large scale. A detailed analysis of the CSI structure and each single receivers, as well as a comparison between the CSI collected at different receivers, enable the attacker to determine the precise position of the person in the room. The attack considered in this paper extends the techniques described in 21. The attacker collects a set of CSI traces with the help of the collaborator standing in specific target positions. Then he trains a convolution neural network CNN with the collected data to use later in order to determine the position of an unaware victim, for example, an employee or collaborator. Figure 2. 802.11 modified the receiver to infer people location. Each receiver collects CSI and pushes everything to localization system. Multiple CSI data originating from the same frame are fused to improve the accuracy with respect to single receiver configurations. The experimental facility. We carry out the experimental in the laboratory of the ANS group at the University of Brescia, whose map is shown in figure 1. 5 receivers from RX1 to RX5 are positioned on task aligned along three of the four sides of the rack, while the transmitter TX lies on the desk on the fourth side. We assume that the attack controls all the receivers and knows that their positions with respect to the transmitter. That can be of the access point of the collaborator network. The goal of the attacker is classifying the position in the person on the 8 possible positions within the room, P1 to P8. This configuration ensures that the person being tracked is always obstructing the line of sight (LOS) between the transmitter and the least one of the receivers. In this way, collected CSI should always be significantly affected at one or more receivers, independently on the victim's position. Third, CSI-based localization and its obfuscation. The principle behind the location technique is the interaction between the Wi-Fi signals and human body. In fact, the presence in the environment of a human body that observes, scatters, and reflects electromagnetic waves induces peculiar variations in the spectrum of the received signals that depends on the body position and the movement. This variation can be studied by analyzing the CSI evaluated by every Wi-Fi device upon receiving a frame. As we shown in figure 2, the correct decoding of frames data requires an equalization of the spectrum of the received signals to reduce the distortion introduced by the communication channels. Extracting the CSI data from the cheapest internals, one can directly observe the modification that depends on the position of observed person, given that the rest of the environment, including the position of the transmitter and receiver, remains relatively stable over time. The localization frameworks that have received more attention are based on NNs trained with CSI obtained when someone is standing in a known position. Then during the attack, the victim position estimated by the recognized the same pattern in the CSIs. CSI 26. It is important to capture the large amount of data, not only to speed up the training phase, but also to obtaining multiple CSI snapshots corresponding to the same position of the victim. As this would allow to average out. Figure 3. Architecture of the CNN used by the localization system. Minor spectral variations. This is generally not a problem in modern workspaces, where Wi-Fi signals pervade the environment and the attacker can opportunistically use the signals transmitted by the access point (APs), a corporate network, given that such Wi-Fi nodes are usually in the well-known positions and generated the largest amount of traffic. In this work, we build the multi-receiver localization system on top of what we introduced in 21, where we have developed an efficient implementation for a single receiver based on the CNN with good localization accuracy. A high-level representation of the NN architecture is shown in Figure 3. We consider 802.11ac frames transmitted on 18 MHz channels with single spatial stream encoded using orthogonal frequency division multiplexing (OFDM). Each CSI data point in is array of 256 complex values, one per OFDM subcarrier. After removing the unused subcarriers, 11 at the edge of the spectrum and 3 at the center, we get as input for the CNN 242 times 2 matrix. The first two convolution layers of the CNN shown in Figure 3 are used to extract complex features from the input data by exploiting the similarity of adjacent frequencies in cascade to the convolutional layers. There are 3 fully connected layers. The output of the last layer corresponds to a choice among one of the possible classes. For example, positions that are decided during the training phase, all the layers but the last one, which use subtext functions, use a common rectified linear unit ReLU activation function. Finally, we use the adaptive momentum estimation (ADAM) algorithms to adjust weight of the CNN during the training phase. To consider the CNN achieves a good accuracy, and this is clearly related to the unique and remarkability constant CSI data that are obtained for each position of the person undertaking in the room. Simple reasoning suggestions that a random pre-distortion of the transmitted signals should suffice to disrupt localization accuracy and obfuscating the person's position. In feasibility study presented in 1911, we obtained excellent obfuscation results by placing peaks at random position in the spectrum of transmitting frames, following a simple time collection structure. As a consequence of this coarse manipulation, the presence of the obfuscator could have been detected and eventually countered with a careful analysis of the signal. Furthermore, the communication performance when an obfuscator was active was severely degraded, leading to highly reduced throughput, improving localization with multiple receivers. The literature on CSI-based localization has so far considered only system with single receiver, but combining figure for the network trained with different types input depending on the considered scenario. When we apply the CSI data fusion techniques or the collected CSI are fed to a single NN. CSI data collected as multiple receivers seems a promising extension to improving improve the accuracy. With enough receivers, it is possible, in fact, to always have at least one receiver whose loss to the transmitter intercept the person under tracking. For instance, if a target person stands in portion P7 in figure 1, we expect minor interference effect on RX1, but clear effect on RX4 due to the obstructed RLS. One of the goals of this work is to extend the localization system by combining the CSI captured at multiple receivers as shown in figure 2. The second one is showing that also this power attack can be encountered. We present two methods for combining the localization data. We discuss here their pros and cons while we present the experimental result in section 6. Common to the two methods is that receivers are positioned in the same indoor environment and have capability matching the reception of same package. We use timestamps, but other techniques are just fine. Majority both. In this implementation, we combine the output of multiple standalone localization systems. For example, one receiver is associated to one CNN, given that receivers in the room are located several wavelengths apart from each other. We assume that the CSI vector at the input of each localization system, which we reported in figure 4, 242 times 2 matrix is independent from the others. Does CNN actually run and classify independent models so that errors are independent? And we can assume that assuming the result compensates the random errors. Unfortunately, position can be assumed in an algebraic way, but we can decide this based on majority of decision, given that position errors are independently by construction. Majority both also correspond to maximum likelihood estimation (MLE) and should be optimal given the assumptions. Let NR be the number of receivers independently from NR. It is always possible that the both does not have a majority. For example, 3 receivers have classified 3 different locations, and no decision can be taken. With separately wrong classifications, a decision is taken, but it is for wrong positions. From undecidable situations when no classification is possible, CSI data fusions, a more sophisticated use of the information at different receivers, is based on the fusion of the CSI vectors, assuming that an extended CNN can do a better job than simple majority voting. Note that majority vote is MLE, but only under the assumption independent decisions. The data fusion changes the acknowledge based on the estimator. Thus, we can hope in a more powerful techniques. In the second implementation, we consider extended CNN that process the CSI vectors collected at the NR receivers fused and the large data set. For example, NR 242 times 2 matrix, as we shown in figure 4. Differently than the first implementation, this method always takes decision for a specific position, as the case of the single receiver, as it does not undesirable situations. We have not attempted to design a new CNN for this task, so whatever the result we obtain, we cannot exclude that a different learning method based on CNNs or on different techniques can obtain better results. Principles of CSI randomization and its implementation. While any approaches that can improve the localization accuracy represent a positive result, at the same time, it can be considered an increasing hazard against the privacy of the trackered people. In addition, an improved localization techniques can also have detrimental effects against the simple obfuscation techniques like one that we introduced in 21. The goal of this section is hence to design and implement obfuscation techniques that can be effective independently of the number of involved receivers. Here we study how to defeat two CNN-based localization mechanisms introduced in Section 4 to restore the privacy of the trackered person. Our good obfuscation techniques is as unobtrusive as possible, effective in preventing localization, and also maintains good communication performance. As discussed in 21, the frequency dependent amplitude of the received signals is the feature that is mostly considered by the CNN is classifying CSI and mapping the person location. For this reason, we focus on randomization techniques on the amplitude of the subcarriers that compose the spectrum of the transmitted signals. We also consider a single transmission chain for the sheer simplicity. The extension to multiple transmission chains is left for the future work. Let NSC be the number of carriers used by the Wi-Fi OFDM modulations FI I equal 1 to NSC. The carrier number K equal 1 to discrete time index identifying the frame, and delta K, the obsolete continuous time between frame K and frame K-1 delta K is undefined, but it is relevant for our purpose. We only consider carriers that are supported by the system, thus excluding the middle carriers and thus in the guard band. The magnitude of the spectrum at the receiver or CSI delivered from the number of initial symbols of the frame represent the frequency and the time-varying signal attenuation or channel response introduced by the channel ARFK. Notice that the entire Wi-Fi physical layer is based on the assumption that channel coherence is long enough to guarantee that channel response in constraint during a single frame. Thus, our model does not introduce significant approximations. The goal of the obfuscator to guarantee that the information in ARFIK does not allow the attacker properly classify the position of a person in the room. Ideally, the obfuscate should guarantee that the mutual information between the CSI and the location of a person in the room is zero, but the theoretical analysis is out of the scope of this paper. To achieve this goal, we multiply the IQ samples of the digital signal before performing the inverse fast Fourier transform IFFT conversion of the OFDM symbols, so that the actual CSI information at the receiver is where times is the standard algebraic multiplication applied separately carrier by carrier. AOFIK is a pre-distortion mask whose goal is adding random information ACFIK so that ARFIK maintains the properties that allows demodulation and correct decoding of the frame given in CSI, but information on the real channel response is degraded to a point where localization is not better than random guess. The pre-distortion AOFIK must have the following characteristics. It does not alter the frame power. AOFIK K equal A means that if the frequencies are amplified, then others must be attenuated with the Ka some appropriate constant. Second, it guarantees that the correlation in time is compatible with the standard movement of a person in a room. 3. Guarantee that the attenuation in frequency is compatible with the channel dropper spread. It cannot be inverted within reasonable time. For example, given in the sequence ARFIK K equal H plus T, it should not be possible to reconstruct to the sequence AO. Not even when using multiple receivers, H is a design parameter whose impact on system is left for future study. It does not modify communication performance of the system. The formalization and, if possible, the proof that the 5 conditions above are feasible are beyond the scope of this work. In the following, we present a heuristic Markovian methodology that we evaluated in section 4. Let R be the vector-independent continuous random variables rho I of dimension n SC, one of the OFDM subcarrier. Each random variable is drawn from the same distribution FR rho, and they are all independent of one another. For reasons that will be clear shortly, we select FR rho to be uniform distribution. With support rho mean, rho max, consider regions be clear shortly. We select FR rho to be uniform distribution. We support consider now the multidimensional random process defined as equation 3 defines uniform Markov process, which compares with the more popular Gaussian Markov process. UGB uniform increment takes from the FR rho instead of Gaussian increment. The dimension of the process, NSC, the process is discrete time, because the transmission of frames defines a discrete time index. However, the process memory depends on the absolute time, delta tk, in order to guarantee that frames transmitted far apart in time do not have excessive correlation. As it is known from probability theory, this process exhibits the dependence in time that increases when alpha decreases, which allows tuning the obfuscation to the expected movement of the people in the room. For instance, the error of global navigation satellite system positioning is normally modeled with a 3-dimensional Gaussian Markov process. The random process defined by equation 3 has no correlation in the frequency domain, which is constrained with the desired characteristic 3 defined above. To overcome this unwanted feature, we use a simple convolutional filter as follows, where star is a standard convolution sum and zeta C is a systematic filter with length C. C must be odd for the symmetry 3C and SC. The dependency of the Fi is implicit in the convolution, and appropriate leading and trailing 0 must be appended in RK. To allow the convolution, the shape and characteristics of zeta C can be studied to optimize the performance. In this work, we do simple moving average or coefficient R1 with C equal 5. Equation 3 and 4 together with the normalization second to be run every step defined. In our opinion, on appropriate randomized localization obfuscation that respects the characteristics illustrated above, the rho mean, rho max, alpha C, and the values of zeta C taps can be used for tuning the system, and can also be changed over time to make it harder for an attack to invert the obfuscation. A proper sensitivity analysis of all the parameters is not feasible within a single paper, and we are more interested in fundamental properties than in finding optimal setting, which may also depend on considered scenarios. A quick preliminary study was sufficient to select rho mean equal minus 0.3, rho max 0.3, and alpha 0.2 for achieving acceptable performance. Notice that alpha 0.2 means that if delta t k upper s, then h0 and AO k-1 are almost completely uncorrelated. The correlation coefficient is below 5%, which is coherent with the requirement. Above equation 3 and 4 cannot guarantee that the distortion does not lead to amplitude smaller than 0, which is obviously not implementable. Also, 0 or very small values are desirable, and they imply that the entire subcarrier is suppressed, which introduces systematically transmission errors that should be avoided. To prevent this possibility, we use a simple clipping function, max-min, that cuts amplitude of each subcarrier between min and max value. Ideally, only the main clip necessary to avoid negative and too small values, but this asymmetry makes it difficult to guarantee that the average power of frames is not altered. Furthermore, the clipping can apply before or after the convolutional filter of equation 4. Predicting the consequence of clipping before or after the filter is very difficult. Because clipping is highly nonlinear, thus we decided to explore the performance of both options, implementing the equivalent of the following two equations. As for the clipping values, we explored two possibilities: a symmetric case with min 0.1, max 1.9, and a symmetric cases min 0.1 and max where we only guarantee that the maximum power density over the frame spectrum doesn't exceed the values achieved by non-obfuscate frames, but we cannot guarantee that average frame power is maintained. Implementation. We describe here some implementation details, focusing on the constraint that may approximate formulas. Introduce figure EDCF application factors assigned to OFDM subcarriers in equation 5 and 6 with both symmetric and asymmetric clips. Blue lines refer to equation 6 and red ones equation 5. No max means max. Above, first of all, we note that NSC 256 edge work with 80 MHz 802.11ac frames. Second, we implemented the receivers using code access point from ASUS. We choose a RT-A6U model. It can extract CSI data from the transmitted frames. Third, we implemented the transmitter with the ETUS USRP N300 software-defined radio SDR, whose bandwidth exceeded the 80 MHz requirement. We choose an SDR because we need precise control over generation of the Wi-Fi frame in order to craft and apply the pre-distortion that modifies the CSI. We generate Wi-Fi frames with the MATLAB WM toolbox running on the workstation we kept with Intel Core i7 and 16GB RAM. We also prepare obfuscate frames directly in MATLAB before sending the corresponding sequence of IQ samples to the SDR, as the SDR does not run on the MEG algorithm. There could be some uncontrolled collision on the channels, even if when we have selected channels 157 that is not used in our university. The MATLAB code implementation of obfuscation techniques described by equation 5 and 6 by applying the pre-distortion in present before the IFFT that is in the frequency domain. We avoided working in the domain because it would require the usage of circular convolution. Before sending the stream of IQ samples to the SDR, we normalized them to the highest value. For example, we divided them by the by 1 with the largest obsolete module. So then we use the entire range of the SDR. We highlight that the overall procedure cannot strictly guarantee that the frame power is not altered as required by equation 2. This entails evaluating the power spectrum of the entire frame, which we are unable to do. However, we deem that the pre-distortion, especially with the symmetric clipping, does not change significantly the power spectrum on the channel. Figure 5 shows the ECDF of the marginal distribution of the amplitude of the process described by EQ7, clip and filter in red, and EQ6, filter and clip in blue. The ECDF is computed over 1000 frames, or equivalently 256 times 10,000, 2,560,000 samples. The solid lines refer to symmetric clipping. Their median value is 1. As expected, as OFDM modulation is not constrained in envelope and its peak to average ratio depends on the payload, as can be as large as 12 decibels. Pre-distortion that preserve the average amplitude should not alter significantly the power spectrum after modulation, but this aspect required further investigation. The dashes line, no max, refer Figure 6, magnitude of the CSI collected from the 800 frames, with a person standing in positions P1 and P2, brighter yellowish color mean larger magnitude. The two plots at the top refer to clean transmissions. The horizontal band shows that CSI are constant over time in the person does not move, enabling localization by ML, machine learning. The two plots at the bottom refer to the same positions when the obfuscation is on. The middle one with filter and clip, and the bottom one with clip and filter. Instead, to case when clipping is applied only to mean amplitude, and the medium is obviously not one, but we do not know if this alters significantly the frame's power spectrum. The counter-intuitive behavior of the solid red curve, clip and filter deserves a final comment. Indeed, by first clipping and then filtering, we introduce multiple discrete components and not two as in filter and clip. In the distribution, they are given by the contributions of clipped subcarriers in the 5-tail average filter and are reflected in the ECDF. Figure 6 reports qualitative result measured at the receiver. It visually shows why Wi-Fi sensing can locate people and why the proposed obfuscation techniques is valid countermeasures. Without obfuscation, the channel response amplitude of the CSI is remarkably constant over time. X-axis, the CNN can run and classify the position of the person. Obfuscation instead keeps changing the CSI amplitude, thus preventing proper running and classification. We would like to record that all the software we have used and the data we have collected are available on our website. Experimental result. Table 1 presents the experimental localization accuracy. Overall, we collected 5 times 8 times 800, 32,000 frames for training the system. 5 times 8 times 100, 4 times 4,000 for testing. Training and testing are done separately, both the clean case and for each obfuscation techniques. 5 different cases in total, and separated by reasonable time of a few tens of minutes at least, so that training correspond to realistic attack and the risk of the localization result obtaining by the chance. Because of the time correction, between training and testing minimized. We merged the collected in different positions by post-processing the acquired traces, thus reducing the number of experiments to be performed. Also, this allows applying the two different multi-point localization techniques. See section 4.A and 4-B. So 4/B extractively on the same measured data, thus avoiding the difference observed in the two techniques is related to difference in the experimental environment and the intrinsic property. Since we consider A possible positions, a random guess would lead to an average accuracy of 12.5%, and this is our reference for evaluating the quality of the obfuscation. Analyzing the data for each single receiver highlights the top of subtable in tab 1, as we already observed in 12.22, that the position of the receiver influenced the localization performance. RX5 performs much worse than the others, while RX3 significantly better. Furthermore, the observed that the localization accuracy decreases with every obfuscation techniques regardless of the position of the receiver, and the symmetry clipping offers superior performance. Although we do not have a formal explanation of this latter fact, while a thorough explanation of the behavior deserves additional research, we speculated it is the same phenomenon that makes the filter and clip obfuscation working better than clip and filter. Actually, obfuscation achieved by filter and clip is almost perfect, with only RX2 scoring of better accuracy than a random guess, 28%, yet hardly usable for any meaningful insight on the location of the person. We will see later that this comes at the expense of the achievable throughput, and we deemed that both results are related to the discontinuity introduced in the spectrum when clipping is performed at the rest operation, which means that some high frequency harmonic disturb the signal, although this can be easily observed on frame-wise analysis. Coming to results achieved with the multi-receiver attack, the first thing that emerges is that a simple and traditional majority voting outperforms the apparently more sophisticated data fusion approach, which does not seem to improve the performance even in absence of obfuscation. As we already commented in section 4, this does not exclude that some other data fusion techniques may outperform majority voting. But with just improving CNN-based localization, simply adding information may be more difficult than expected. A possible explanation lies in the fact that the data fusion approaches does not make the localization errors of different receivers independent of one another. Thus, the strong correlation in the data induced by the CNN makes some errors dominant. The result parentheses for measuring voting in tab 1 are percentage of an undesirable situation. For example, a majority decision has not been reached. As expected, these are particularly high when considered only two receivers. While increasing the number of receivers increases the performance and decreases the number of undesirable cases until localization without obfuscation becomes perfect. For n equal 5 receivers, and we cannot consider the localization deterministic also with 4 receivers. Notice that given the amount of data we collected, the absence of even single misclassification makes the result NR5 extremely reliable and significant. making Wi-Fi based localization a true threat for localization privacy. For NR5, the results reported for average overall possible combinations of 5 receivers in pairs, triplets, and quadruplets against make the result highly reliable, and indicating that multi-point localization also makes the techniques less sensitive to the receiver positions. Considering the obfuscation result, it is immediately clear that the techniques we proposed is robust also against a sophisticated attack brought with 5 receivers strategically placed in the survey rooms. Against the filter and clip techniques completely obfuscate the locations, indeed making it even worse than random guess and outperforming and other strategy. Note that when obfuscation is active for major voting, there is a high percentage wrong decisions. The sum of the percentage reported as more than 100%, which were instead completely absent without obfuscation. This is a strong indication that randomized predistortion implemented by the obfuscation successfully deceived our localizer, so that it does not run anything nearly meaningful during training phase. In spite of the fact that obfuscator is on, does the classifier record that the CNN running is supervised, so training should be effective is in any case if there is information to exploit. Indeed runs random patterns, and it is not able to single out channel characteristics.